chapter 9 in your book. And this is a concept that you basically know from other courses before geotechnical engineering, where you're just applying the concept to soil in a particular case. In situ stresses, first of all, you have to remember that the soil is every type of soil is a multi-phase system because it's integrated by liquids, solids, and voids. The voids might be either occupied by water or by air or by a mixture of water and air. And the in-situ stress of these soils, you have to analyze it because when we are dealing with problems like compressibility and compaction, and we are talking about settlement, and we are talking about bearing capacity of foundations and stability of not only of embankments but slope stability also, and lateral earth pressure on earth retaining structures, and so many other problems that we have to solve. And all of those problems are directly related with in-situ stresses. When we are talking about, once again, right now in-situ stresses, we are referring to normal stresses. This is the part that we are dealing with in this chapter, normal stresses only. Let's start by trying to analyze this figure. And when you see this figure here, basically what you have is a soil in this part which is saturated. How do you know it's saturated? Well, because the water content is here at these points. The whole soil is saturated. And if we are interested in calculate the stress at this particular point A here, that stress is going to be basically due to what? To the weight that is on top of that. That's basically it. All the pressure that is applied to that at that point is coming, pressure, stress is coming from the pressure that the soil is acting onto that point, as well as the water. So we have two parts that are going to conform that one. The first part is this height of water, only the column of the water here, multiplied by the unit weight of the water. That will give you basically the pressure here, or the stress at this point due to this. And on top of that, we have this other column of soil, which is saturated, as we say before, saturated. And this height of the column is HA minus H multiplied by gamma saturated. If you add this plus this, of course you will be getting the stress at the point A. Now this stress can be and is divided in two parts. A portion carried by the water, which is not only this, because remember this is saturated, so we have water here and we have water everywhere here. All these pores are filled with water. And that's the first part, a portion carried by the water, which is called the neutral stress or the pore water pressure stress. Pore water, the stress that comes due to the pore water pressure. And the rest is carried by the soil solids when the grains are in contact in between each one of them. In other words, let's say that we want to calculate the stress, and for that, and in this section, and for that we're going to take an arbitrary section like we are showing there, AA. The first part, which is only the stress that comes from the grains in contact. Remember, we discussed that in class before. You have grains of soil and grains of soil. That point of contact between those grains of soil, I'm going to have water here and water here also. But the solids itself, the contact between the two parts of the solid, which is what we are showing here in this part, that contact is going to provide between this grain and the other grain that you have at the bottom, at this part, they are going to produce normal forces, normal to the surface of contact. And because we are interested in vertical stress only for this part of the chapter, the vertical stress is going to be the vertical component of this force P1 plus the vertical component of this force P2 plus the vertical component of P3 plus P4 plus every single grain in contact. Of course, that is very difficult to calculate. As a matter of fact, you can't calculate that. That's why we derive the effective stress. But anyway, let's try to derive a formulation for that. So we have the vertical component of each one. Because we are referring to this cross-sectional area, we're going to divide that exactly by that area, by the cross-sectional area that we are analyzing. That will be the effective stress. That stress is called effective stress because it's a stress that is, let's say, intergranular stress. Contact between two different grains of soil at that particular section that we are studying. Now, if you know that the point of contact between the two grains is this A1 and this A2 here, and this part A3 and this part here A4, that is the contact between this grain and so on, just the part, that part, and I know the total cross-sectional area is this A bar, then I can infer that everything that is not soil, in contact with soil, is going to be the area of the water. So I can subtract the area, the total area, which is the cross-sectional area, minus that contacting area, intergranular contact area between the grains. Now, if this is that area, remember effective stress is the one I just calculated here. This is the total stress. This stress is called effective stress. Contact in between grains. And then the other stress coming from the water should be the pore water pressure at that point multiplied by the area of the water, the surface area of the water in that section. What happens is that we are normalizing it again and we are dividing it by the same cross-sectional area that we calculated this from. When you do that, you just divide this here, take common factor u, as we have before, this a and this a cancel out, and then we are referring to this new value, a prime s, which is just the area of the solid divided by the cross-sectional area. U, of course, is the pore water pressure at that point. Notice that at this point that we are referring to is HA times gamma W. Not only this H, the total, because I told you the whole soil is saturated also. So the pore water pressure at this point is the total height that we are analyzing multiplied by gamma of the water. A prime S, as I defined it before, is just a ratio between the area of the solid and the cross-sectional area of the soil. And of course that value is going to be really small because the contact area in between grains are going to be small also. That means that we can neglect that value. If we neglect that value, we get one of the most important equations. It's simple, yes, but it's one of the most important equations that we have when we study vertical stresses in the soil. It tells you that the total stress is equal to the effective stress plus the pore water pressure stress. And the important thing about this is that the total stress is very easy to determine. How? Because it's just the accumulation of all the weights on top of the point that we are studying, or the area that we are studying. When I say weights, remember, it's not the weights, the weight divided by the area, but you get the message. And the pore water here is the same thing, so it's the pressure of the water also at that particular point. So we can derive from here the effective stress. And the effective stress is the important one. This is the one that affects everything in the soil. And you will say, why? Because this effective stress here is okay, imagine that you are now, you remember trusses, I hope that you remember trusses from your static classes and structural analysis classes. When you have a truss in the air right now, at this atmospheric pressure, and you have a truss subject to loads, you analyze that truss and calculate the forces in the bars, the elements, the members, that you remember that those forces are tension or compression forces. That's basically what you can get there if everything that you learn about trusses is correct and you kept all the concepts about trusses, like remember smooth beams and loads applied at the joints, etc., etc. Now, if you get that very same truss, and that very same truss, you submerge it in water, and apply the same loads to that truss, guess what? Well, you shouldn't have to guess, you should know it. But anyway, guess what? the internal forces, tension and compression forces, axial forces in that truss are going to be exactly the same that if you compare them at the atmospheric pressure. That's the, I would say, the closest analogy that we can get through this effective stress. The contact in between the grains. That's the important part. If those grains slide in between them, you don't have the contact, necessary contact, you don't have that stress, you will have settlements there also. What is resisting the total weight of the structure that you can place a foundation on top of that is directly linked with the vertical stress, not with the total stress, not with the pore water pressure stress. Going back to the original reasoning from this figure, remember we say that the total stress was this part of the water plus this part of the saturated soil. Well, now we are going to just put the total stress, which is exactly what I told you, H multiplied gamma of the water plus HA minus H gamma saturated, and we are going to subtract from here the pore water pressure at this point, and the pore water pressure at this point, or the stress at this point, is the total H multiplied by gamma of the water. That's effective stress. Now when you just solve these and group common terms, you can see that you have here H gamma water, you have here H saturated also, and if you remember, H gamma water minus H saturated, or gamma water minus gamma saturated, or vice versa, gamma saturated minus gamma water, when you reorganize the equation, what you have basically here is what? I know I don't have any student, but I can't help it. I can help to ask questions. What is gamma saturated minus gamma water? At least answer it in your mind. Yes, that's it. That's gamma submerged. So basically, for this particular example, you can calculate the effective stress just by getting the height of the column of soil multiplied by the gamma submerged of that soil. This depends on the type of cases, okay? I'm referring to this particular figure. But by the way, in some of the FE tests that I have seen, this is asked, this particular type of problems with effective stress. So you better understand this before taking the FE. Okay, now let's go back to the laboratory. Now we have this here. This is just an experiment that we're going to do. We have remember, the pore water pressure here, the piezometric is going to be the same, depending at the same level. The column of water has to be equal to this one. And the valve is going to be closed. That means there's no seepage. Remember seepage, right? There's no flow of water, not in or out flow of water here. So there's no seepage. If we want to do that, we can show the total stress at these 3 points. The total stress at this point, of course, is going to be 0 because that's what you consider atmospheric pressure. When you go to the point A, the total stress at the point A is going to be defined by the height of the column of water, because I don't have anything else, multiplied by gamma of the water at this point. What is going to be the total stress at H2? We just calculated before. It's going to be the height. It's going to be this one, because it's a cumulative process. So you can say that the stress at the point B is the stress at the point C plus whatever this portion of the soil is adding to that stress. Well, whatever this portion of soil is adding to that stress is H2 multiplied by gamma saturated of that soil. And same thing at this point, it will be the stress at this point plus Z times gamma saturated of that soil. That's exactly what we have here. You see, H1 is H1 gamma of the water at this point. At this point, it's going to be whatever I had before, which is H1 gamma of the water, plus this portion of the weight of the saturated soil, Z gamma saturated. And at this point, it's just the same thing. We can take this and add it at this other part, or we can take this and add this column of soil. That will be H1 gamma water, this point, plus H2 gamma saturated. That's the total stress, and I hope you don't have any problem with that, because that's old knowledge. This is nothing new. Now, Remember, our objective is calculate the effective stress, vertical stress. The effective vertical stress is going to be the total stress minus the pore water pressure stress, or the neutral stress, the U value. And the U value is just the stress produced by the water, normal stress. Normal stress, remember, shear stress doesn't apply to liquids, normal stress. Now, at least doesn't apply to water. If you have, or to fluids, if you have, let's say the U now, the pore water pressure at this point is going to be 0, of course, because that's atmospheric, once again. At this point, the point A is submerged, the distance h1. So we're going to have h1 times gamma of the water. At this point, everything is submerged, so if I calculate just the water is going to be h1 plus h2 times gamma of the water, as you can see here. Now, how do I calculate the effective stress? I just subtract this minus this. How do I subtract that point by point? The first point would be 0. The second point would be, oh, guess what? 0. Does that make sense? Does that make sense that the effective stress at this point is 0? Of course it makes sense. Why? Because there's no soil, and effective stress is just provided by the intergranular stress between the particles. That's it. There's no particles, there's no soil, so this minus this is going to be 0 also. And at this point, when we subtract this minus this, what you're getting basically is what we said before, is the effective stress is going to be the height of the column of the soil multiplied by the submerged unit weight. When you don't have seepage. If you have seepage, this is affected, and this is affected by the seepage, as we will see soon. Let's do this example. In this example, we have to calculate the total stress, pore water pressure, and effective stress at the points A, B, or C. Well, this is basically the same thing that we showed in this previous one. So let's start by checking and seeing what is this problem about. You have 6 meters of dry sand. How do I know it's dry sand? Because they are telling me it's dry sand. I don't have any moist content here. I don't have anything. It's dry sand. The water table is located at this level, and everything below the water table, remember, is saturated. So you have dry sand here and saturated sand here. Why do I need to know if it's dry or saturated? Because depending on the unit weight, the stress is going to change also. Now let's start with those 3 diagrams. Remember, total stress, pore water pressure, and effective stress. The total stress at the point A, this point. How much is the total stress? 0. I don't have anything. How much is the water pressure at the point A? 0. I don't have anything. And 0 minus 0, well, it's going to be 0. So that's why you have 0, 0, 0 at this point. Now at the point B, this point. Point B, total stress is the summation of everything that is on top of that point B. But what I have on top of the point B is dry sand. Basically, the total stress at the point B then is going to be this unit weight multiplied by 6. That's what we have. That unit weight multiplied by 6. This is the total stress at the point B. What is the pore water pressure at the point B? No, how is it going to be 6? It's not 6. How is the water pressure at the point C? At the point B? There's no water here. So the pore water pressure is 0 at that point. And then in order to obtain the effective stress at B, we subtract this minus this, and we get the effective stress at the point B. And we plot our 3 points, 3 corresponding points here, here, and here. Last but not least, we have at the point C now. Well, our stress at the point C, total stress, is going to be basically whatever we have up to the previous point, meaning this value, plus the weight of this column of soil here. This column of soil is saturated. And even if you don't say saturated sand, you have to know it because it's below water table. What is the weight of this saturated sand? It's going to be this unit weight multiplied by this depth, 13. But remember, this is just what is happening in this layer. I have to add everything that it was on top of B. And that's what we do basically here. We take the value that we had before, which is 6 times gamma dry. That was the value that we got before, the 99 that we got before, plus the 13, this part, times the saturated unit weight, and you get the total stress at the point C. Now, what happened with the pore water pressure or the neutral stress at the point C? Well, this is the part that is submerged now. Pore water pressure comes only from water, so it's going to be 13 times gamma of the water. 13 times gamma of the water. And effective stress is going to be this value minus this value. That will be our effective stress. I put my 3 points and plot my diagram. These diagrams are important because then with this diagram is used for several things, or these values are used for several things. First, as I said before, for stability, for compressibility, for compaction, for bearing capacity of the foundations. But at the same time, because the water doesn't produce, this part is not affected by shear stress, only the soil, we use, not in Geotech 1, but in Geotech 2 you're going to see it, and also in the FE you could have a couple of questions about that. But I'm going to do a review for the FE later. But you use this effective stress and modify some friction factors and convert it in lateral stress then, the same one. You use it for that. Okay, another example. Look at this one. It's a plot the total effective and neutral stresses also. And then you have this part. In case you haven't noticed it, well, let's first analyze this. You have the first part, you have this sand here, you have your dry density and porosity, the first 2 meters, and then the same type of material, the same sand continues for 2 more meters, but it's the same, but it's submerged in this case. Look at the water table, what it is. And then you have another layer of 4 meters of clay with this dry density. And then we have to calculate the effective neutral stresses at the 3 points. What I say, in case you haven't noticed it yet, you need to know your what? Your 3-phase soil diagram for calculating the vertical stresses also. So the first thing that I have to know is I have these values for these, but I need the saturated dry density. Saturated dry density, I have an equation. You can do your 3-phase soil diagram that says that is the dry density plus n times density of the water, and that will give me the saturated density of the sand for this part. Once I have that, I go to my original diagrams. Remember, this diagram, what it's showing is the depth versus the pressure or the stress, how the stress is varying with the depth. At 0, how much is the total stress? 0. At 2, the first 2 meters, the total stress is given just by the weight of the dry sand, so it will be 2 meters times this density times what? Times gravity. Very good. So you have 2 meters times the density times the gravity, because this is density, not unit weight. And we're talking about stresses, so we need unit weight. And we have the first point. Now, what about this point? You just have to get this value that we had before and add this weight. What is this weight? 2 meters multiplied by what? Very good. I gamma saturated, which is this one, and multiply by, once again, gravity. So you have the 2 meters times gamma saturated times gravity plus the value that I had before. That would be the value of the total stress at this point. Now, what about these other 4 meters? Same thing. I take this value and I add these 4 meters of saturated clay. Add those values, that value, plus the 4 meters of saturated clay. Remember, always multiply by gravity, and you get this value, and you get your first diagram. If you look closely, this diagram is an accumulation of weights, if you will. It's an accumulation of weight. So it's impossible for this diagram that this point here is bigger than this point here. This diagram can never ever go back here. That just don't happen. Doesn't make any sense, because unless we are living in an alien world, I don't know, this is always going to weight more and add weight to this point. And I'm telling you this because, and when we go to the test, I'm pretty sure that I'm going to see that. How do I know? Because I have been seeing it forever. And even though I do the clarification in the lecture. Okay, now, pore water pressure. Pore water pressure at this point, 0, there's no water. At this point, it's still 0, there's no water. At this point, 2 meters times unit weight of water. And at this point, 6 meters times gamma of the water. 2 meters times gamma of the water, or I can say 19.6, which is the previous times 4 gamma of the water, is the same thing. Or I can say directly 6 gamma of the water. And I have my gamma of the water, my pore water pressure. Now I subtract point by point. First point 0, second point 26.46, third point 62.78 minus 19.6, 4 point this minus this. And that would be my effective stress at that point. Notice that the slope changes, but it's never gonna change to the left. It's a change in the slope, but not in a change in the sign of the slope. Okay, when I do this in the classroom, I used to ask for this particular problem, and this particular problem, I'm gonna ask you to do it also, but I'm gonna kind of clarify a little bit what is happening here. It's a salt section as shown in the figure has a perched water, a groundwater level. This is what is called perched. This is a pocket of water, but it's not only water, it's water with sand. It's a submerged pocket of sand. Plot the total and effective stress and pore water pressure with depth along the sections AA and BB. So you have one section here and one section here. I'm going to switch to the camera document so you can see something. This is basically what we have over there in that part. You have at this point this type of soil, and this type of soil has a water content of 12% and a percentage of saturation, degree of saturation of 0.9. But if you look at this first section, the first section that we have to analyze is a section that passes through this part. Let's say this is my section AA. Here. This is the section AA. If I have to study this section, look at this. This soil, everything here, everything in this part is exactly the same. So if I have to do my diagram for this, of course, the first thing that I have to do is calculate what are the properties of this soil. And you can calculate the properties of this soil because you have the water content, you have S, if I'm not mistaken, you have GS also. See, yes, you have GS. GS is 2.7. So you can calculate the properties of this particular soil because you can calculate the gamma. Once you get the gamma of this soil, and this is gamma moist, remember, it's not dry. It's not dry because we have a water content. So you can calculate that gamma. Once you have that gamma, the only thing that you have to do is calculate your pressure. Everything here is moist sand, but there's no water. This doesn't mean that I have pore water pressure. In order for this to have pore water pressure, it has to be submerged. So basically, what I have is this for my total stress. And then here I have a different type of material. It's basically the same GS. This is the water content, but it's saturated. So this is a saturated gamma here, because it's below the water table for this part. So we're gonna have another diagram, something like that. This is the total. For the same section, if I have to do the U for this part, my U for that part will be something like 0, 0, 0, 0, 0, 0, up to this point. And then the U is just gonna be this little part. This is the U for the section AA. This is the same problem that we did before, basically. You're gonna do it, okay? You're gonna solve it, you're gonna try to do it if you want to. But I will advise you to do it. Then you subtract point by point and you get these values. Now, for the, and this depth here, I didn't copy it before. That depth is 3 meters, but it's in the slide that I was showing before. This is 3 meters. Now, the other section is the interesting one. Well, both are, this is not, it's not that it's not interesting, but the thing is that we are cutting this perch water here. And this is the section that we call BB. At this section, if I want to do, let me zoom this a little bit. There. If at this section I have to do a total stress at that part, look what is happening. At this point, the total stress, of course, is going to be 0. At this point, I'm going to have this total stress, but I'm using this gamma times these 3 meters. This gamma times these 3 meters. But when I enter at this portion, the gamma changed, because now this gamma here is going to be also a gamma saturated gamma. Same thing with this saturated gamma. They are different, saturated gamma, because the water content here is 8% and here is 18. But no matter what is a saturated gamma, I'm going to call it saturated gamma 1 and 2, so you don't get confused. So this part is going to apply this weight plus the 3, this weight plus the 3 times the saturated gamma, times the moist gamma, this moist gamma, okay, here. But now in this other part, I'm going to add, what I'm going to add here is the saturated gamma 1 times 4 plus the value that I got before. That's going to be my value at this point here. This, remember, is this plus this goes here, and then I have this other part, and this other part here actually is the same gamma that I had before, because the saturated is just perched here in this pocket. So the soil here is affected by this gamma. So it's going to be, the value at this point is going to be whatever I had before plus this 1 meter times gamma saturated, gamma moist, this gamma moist here. And I go to this point. And when I go to this point, then it's going to be whatever value I have here plus gamma sat 2 times 3. That will be the total stress, which is also really easy to calculate. Actually, there's nothing complicated. It's just a little bit of common sense with what you're doing. Now, when you're doing the U, the pore water pressure, at this point, how much is the pore water pressure? 0, there's no water. At this point, 0, there's no water. So I'm going to start from here. This portion is submerged. This portion is full of water. That means that for this portion, at this point, I'm going to have some water pressure, which is going to be 4 meters times gamma of the water for this value. Now, immediately after, below this value, exactly here, if you look down, you don't have any more water because the water is perched here. So that means that this value goes back to 0. And I know I told you that this one cannot go back, and I still insist in that. It's not going to go back because it's an accumulation of weight. But we are talking about pressure in the water. Imagine yourself with a cup of water on top of your head. You are below the water, right? But you don't have any water pressure here. The cup of water has pressure. It's exactly the same thing that happens here. Now, from this point and this point, you don't have any water, hence you don't have any water pressure. And from this point, you are, again, water table, so you're going to have gamma water times this 3. And this is the other water pressure here at this point. Now you subtract point by point, and you get your prime, effective stress. This minus this minus this. Remember this point, at this point you're going to have a jump in your diagram because you're going to have a value when you subtract this, but if you subtract this point below, you're going to have the same jump in the diagram for the effective stress. Try to go through this problem, try to solve it, and if you have any questions regarding that problem, look for me. But I did much more for you guys here that I usually do because I assign this in the classroom and I make you think through this. Okay, let's go back to effective stress now. Let's keep going and let's keep talking about effective stress. Yeah, this is the problem that we had before. Okay, and this is the problem that I was assigning. You know something? Yes, let's go back and talk about effective stress, but I'm gonna keep using this for a second because I just remember something. Now you have a seepage. No, we have the effective stress, and the effective stress you have the soil, and the soil. In this particular case, you have the water table, and the water table is constant, and nothing happens. But now imagine that you have just the situation where you have a sheet pile here. And let's say that you have the water in this part, and at the other end you have water in this part. Not only water, remember this is water with soil and height of the water, but you have soil here and soil here in this part. What is important about this is if you have this type of situation and the material here, the soil, is permeable, which is going to be permeable, of course, most of the cases. You don't have such a thing like fully impermeable, but let's say it's a granular type of soil mainly. You're going to have, and this is impervious at the end here. Remember that you have your flow nets or flow lines, etc., etc., etc. But the thing is that you're going to have a flow of water coming from this end to this end. And whenever you have a flow of water coming from this end to this end, water, remember we discussed in class about quicksands and boiling effect. What happens is, you remember when we discussed the part of quicksand, and I was explaining the Tarzan movies and saying, oh, it's not like that because you don't get sinking. Basically what happened is, and one of the experiments that you do in the lab also is you have a tank full of sand here. You put a weight, which could be the person in the quicksand. You put a weight here on top of the sand, and you see that the weight is there perfectly. And this could be full of water, no problem whatsoever. This is full of water. Now, if you connect a hose here, a valve, and you start injecting water up, that water is acting against those intergranular pressures in the grains, and it's releasing or relieving the friction in between the grains. Imagine that you have 2 grains in contact here or 3 grains in contact here, and suddenly you are shooting water. The friction between these grains is lost, or is going to become lost. And remember, that happens with the critical hydraulic gradient, happens at the exit, etc., etc. And I'll show you how to calculate it. The critical hydraulic gradient, the gamma submerged of the soil divided by the gamma of the water, gamma prime, gamma of the water. But the fact is, whenever you have this flow of water acting in this direction, that friction is becoming lost. And if that is happening, it's because somehow the effective stress is affected. Now, if our effective stress is, the total stress is sigma equal U plus effective stress, and the effective stress is sigma minus U, the total stress is not going to be affected by a flow of water, because the total stress, if you remember what I told you, is just the weight that is acting on top of the point that I'm in, the section or the area that we are referring to. And we said if we have this type of upward seepage, let's call it now what is called upward seepage, this portion here, if you have that type of upward seepage, and we definitely see the effect of the effective stress getting smaller because of that upward seepage, if this is constant, the only thing that can happen for making this smaller is that the pore water pressure increase. And that's exactly what is happening there. The effective stress is getting smaller when you have an upward seepage due to the increase in the pore water pressure affected by this upward seepage. This is this part. Now if you analyze this part here, it's the opposite. Now you don't have the water entering, you have the seepage coming in this other direction, which basically is acting with the grains and interlocking them even more, increasing the effective stress. Once again, the only way that you have for this to increase, if this is constant, is that this decrease. So for downward seepage, the pore water pressure is going to decrease and the effective stress is going to increase. For upward seepage, this is going to decrease and this is going to increase. Okay, this is what I was referring to before. Effective stress due to seepage. Effective stress increases when you have downward seepage. Effective stress increases. Effective stress decreases here when you have upward seepage. Downward seepage, upward seepage. That happens because of the buoyancy force that now is acting here in this part. If you have upward seepage, which is the case that we were dealing before, if you didn't have the seepage, the only thing that you have is the weight of the soil and the buoyancy from the water. Now you have another seepage force caused by that flow of water going up, and that's what is affecting, and that's why this total thing, which is the pore water pressure, is affected also by that. If you look at the example now, the experiment, once again, you have this experiment in this part. You have A, B, C, the same thing. The valve was closed and the level of water was the same because the pressure was the same at this point. Now if you open the valve at this point and you start having an upward seepage at that location, what is happening with this pressure is that it's changing also. That's what I was telling you. The pore water pressure increases here wherever the seepage is happening, making the effective stress to be smaller. So if you now plot your total stress is going to be exactly the same, no change whatsoever, no change at all. H1 gamma water, H2 gamma saturated here, H1 plus H2, that's it, same one that as before. The change is happening with the pore water pressure. If you see the pore water pressure, at this point nothing happens because you don't have soil, only water, and the seepage happens due to the soil. The seepage force happens due to the soil. So this is going to be H1 gamma 1. But when you go to this point at the end, basically, if you put the piezometer here, the column of water is not going to be H1 plus H2, but it's going to look like H1 plus H2, and it's going to be even higher than that in that piezometer, because you have kind of that seepage that produces kind of an artesian force over there. So you have H1 plus H2 plus H gamma of the water. Now you will say, what is this IC here doing? I don't get that part, and I don't blame you. But what is happening here is this: if you look at any point Z in between, well, if at this point the total difference in head is H, and at this point is 0, basically, not the difference. There's no difference in head at this point. Whatever you are in between is going to be a ratio between this H and the length that the soil is crossing, changing from a maximum here to a minimum here. That's why you have this H divided by H2 times Z, which is the depth. It's a ratio of this H. Now look closely. What is H divided by H2? Oh, wait a second. H, I mentioned it before, difference in head. H2, length of the soil. Difference in head divided by the length of the soil is the hydraulic gradient. That's what this comes from. Now when you subtract point by point, you get your effective stress, which is 0 at this point as before. And at this point, when you subtract H1 gamma water, H1 gamma water, it's going to be 0. Z gamma saturated, Z gamma water is Z gamma submerged, and the rest is IZ gamma water, which is this part here. This is the effective stress when you have seepage at any point. At any point. Now remember the boiling condition and the quick condition. That happens when this is 0. So if this is 0, you can calculate what I defined before in the previous lecture as critical hydraulic gradient, because if this is 0 at this part and you solve for the critical hydraulic gradient, what you're getting basically is gamma submerged of the soil divided by gamma of the water. And that's the one that you have to have at least a factor of safety of 4, 5, 6 against that hydraulic gradient, critical hydraulic gradient at the exit. That happens when you have the, this is what I was just explaining to you right now. An example of this, same thing. Now you have this situation, and you have the boil ratio 0.52 and a specific gravity of solid 2.67. Calculate the total stress, pore water pressure, and effective stress at A and B, point A and point B. First, this is saturated, right? So you have to calculate based on this, based on this. You have to calculate your gamma saturated for that soil. And start with the total stress. What is the total stress at the point A? Total stress at point A is going to be 0.7 times 1 multiplied by gamma saturated. That's the total stress at point A. 0.7, of course, gamma of the water, this part, plus 1, that's the depth, gamma saturated of the soil, 27. At point B, Okay, let's go first with the pore water pressure. Pore water pressure at point A. Pore water pressure at point A, remember that it's going to be whatever column of water I have, 1 plus 0.7, 1 plus 0.7, that's the column of the water, right? But that will be only if you don't have seepage. But now you have an upward seepage happening here. That means that you have to include the ratio of this difference in height. The ratio is 1.5 divided by 2 and multiplied by 1. If you have doubts, remember this part here. This part here that we did before. This ratio. This is the part that I was explaining. And now you subtract this minus this, you get your effective stress. At the point B, it's exactly the same. It's exactly the same. It's 0.7 gamma of the water plus 2 times gamma saturated. Now the pore water pressure at this point is basically 2 plus 0.7 plus this H, 1.5 multiplied gamma of the water. And the effective stress is just this minus this equal that. How much has to be the critical hydraulic gradient for quick condition? That's the other question. We have a formula for that. Critical hydraulic gradient has to be gamma submerged divided by gamma of the water. Gamma submerged is saturated minus water divided by gamma of the water. The hydraulic gradient, critical hydraulic gradient, has to be at least 1.1 in order for that to happen. Now the question could be, is that happening? Well, you can calculate it. Divide this gamma total 1.5 by 2, and you will see that it doesn't happen because 1.5 divided by 2 is 0.75. If the seepage is bigger and this goes, let's say up to 2.2, then it will be exactly there. But for that I have to have more inflow of water. That's for upward seepage. For downward seepage is the opposite. Now what is happening is that I have the seepage force acting down, the buoyancy acting up, and the weight of the soil acting down. If you look at this, now it's going to be the opposite. The inflow is from here, the seepage is going down, at this level is going to be the same, but as I'm going down, this is not here. I don't know what happened here. You didn't see that. This is what happened there, basically. So when that happened, this is occurring here, and basically what you are doing is that the pore water pressure in this part is decreasing, as you can see, and because of that the seepage is increasing. And no seepage, this is the case that we did before. No seepage. You see, how do I know there's no seepage? Because you have the same head both sides, or you have this valve closed. It could be also no seepage. If it's no seepage, it's the very first time that I explained to you the same thing. Now we have a problem also when you have sheet pads. The soil heave actually can cause instability and collapse of those sheet pads. Soil heave can be caused for several reasons. Because you release soil and then you have a stress release and the soil heaves or expands in that part. You can have upward seepage, which is the one that we are dealing with now, for any reason. You can have swelling due to the rotting material that is expanding also, or you can have expansion because you have water and it freezes the water and makes the soil to expand also. Basically, the one that we are interested right now is in this one, because once again, when we are here, remember, this is going up. This is going up, and this soil loses friction for saying it in that way, this is going to collapse. This is going to basically come into this way, this is going to come into the other way, and the sheet pile is going to collapse. It's going to overturn in that part. So Terzaghi in 1922, after conducting some experiments, so many experiments, he determined that the heaving generally occurs at the distance d half from the sheet pile, where d is basically the depth of the sheet pile here. So this is going to be the critical heaving zone. It's a d by d half, but remember that d is the depth of the sheet pile in this portion. If that heaving is occurring here, there's going to be some way that we can avoid that. How do you think we can avoid that? Well, actually we discussed it before. We discussed it before, but we discussed it for washing away the fines. And the answer is we can place more weight in this part. But if I put more weight in this part, how come that is going to prevent it? Remember, then you're going to have like a force building up in that point. So what we do is we put a filter, because a filter is going to provide me with more weight in that part, but at the same time it's going to let the water go freely, and it's not going to allow the washing of the grains, and it's not going to allow up to a certain point, a certain extent, that the soil loses the friction in this part. Factor of safety against heaving is given by calculating just the weight of that soil, the submerged weight of that soil, divided by the upward force produced by the seepage. This value, which is the submerged weight of the soil, is just d, remember the depth of the sheet pile, d half divided by 2, and remember this is multiplied by the saturated submerged unit weight, but remember this is per unit length. We are calculating always, as we calculate these type of structures, we are assuming per unit length. So basically this weight is d squared gamma prime divided by 2. Uplifting force caused by the seepage on the same volume of force. If you have this force acting here, the force is going to be acting in the same volume of soil. So what we have is the same volume of soil multiplied by, what is the seepage force? The seepage force is the hydraulic gradient average happening in this part, multiplied by gamma of the water. Hydraulic average, I'm going to show you later how to calculate it. And the factor of safety, basically, when we divide this by this term and this term cancel out, this and this cancel out, and we only have gamma prime divided by hydraulic average times gamma of the water. That's what we have there. Look at this example. Let's check it really quick. You have the flow net that you have to calculate around the sheet pile, of course. Calculate the factor of safety against downstream heave. Given that gamma saturated for the permeable layer is this, of course, is 112. Thickness of the permeable layer T is 60 meters. This is 60 meters. And this T is given because we have a chart also that allows you to calculate that. I'm going to show you first without the chart, and then I will show you with the chart. Okay. Heave occurs at the distance d half, so this is 20, this is going to be 10, this is 10, this is 20, as I told you before. And we have to calculate the seepage force. The seepage force is prepared by the hydraulic gradient, so we have to check the hydraulic gradient between this point and this point. How do we do that? Well, the driving head divided by h1 minus h2. h1 minus h2 is this. Let's see what is the driving head at the point B. What is the point B? This is the point B. The point B is this part here. And it says that the driving head is 3,6 h1 minus h2. Remember that you're going to have a drop per each one of these equipotential lines from one end to the other end. So if I'm at this point, exactly at this point, basically I have 1, 2, and 3 drops up to this point. You see that? That's why we have 3 over 6 H1 minus H2. That's going to be the head at this point. H1 minus H2 times 3 over 6. Now at point C, it says 1.6 divided by 6. Well, because you can see this differently. You can see this coming from this end, or you can see this coming from this end. If you look at the driving head coming at this end, you have 1, 2. This value between is not 1.5 because it should be here. 1.6. 1, 1.6. Or you can start from this point and say 1, 2, 3, 4, 4.4. And then you see 6 minus 4.4 out of 6. 6 minus 4.4, 1.6 out of 6. H1 minus H2. Once you have that, basically you have the head at this point and you have the head at this point, and that allows you to calculate the hydraulic gradient. The hydraulic gradient, I don't know if you can see it here. Hydraulic gradient is going to happen in this depth here. You have the head here and you have the head here, but that head is going to be changing according to this depth. This is the total soil. So what you're doing, basically you are getting 3.6. 3.6 is the way the book calculated, because the book calculates in between points also and consider this like a parabola equation. But if you get this value and this value, and you put these two values here, this value you put it here, and this value you put it here at this point, and you consider that like a triangle, instead of 0.36, I think you're gonna get 0.358 or 0.362, something like that. So it's basically the same one. I don't know why this refinement is coming into play, because it's not necessary to do it. But anyway, that's the way you do it. You calculate the hydraulic average, and now you can calculate the factor of safety, which is gamma prime divided by hydraulic gradient gamma water. This is just plugging into the equation of average, but we could just solve it for it instead of calculating it. You put this in here, calculate it, and your factor of safety is 1.77, which is not a good factor of safety because we say it should be the 4 or 5. But our question was just calculated it. Now, you can use a table 9.1 in the book. This is the table 9.1 in the book. Basically what you do is you calculate this value, D over T. T is the depth, this T, where I am. This is T. From here to the impermeable layer, that's T. D over T, that's what we are doing. So if we do D over T for this particular problem, is 20 divided by 60, so it's 1/3, and you can enter here with 1/3 and calculate the value of T. You have for 0.3, 0.359, for 0.4, 0.353, interpolation 0.357, and once you have that, you just apply directly this equation, because the rest of the values you have, and you get 1.78. It's basically the same, which is insufficient, by the way. How do you prevent that? How do you improve that? By using filters, and then you increase the factor of safety. 4 to 5 is required, and we mentioned this before for piping. It was 5 to 6 or 6 to 7, 5 to 6 I think, but it's similar. So then we can put a filter. Why? We put a filter in this part. This filter, what is doing this filter? Is adding this extra weight. That's what it's doing basically. Adding this extra weight, but it's not affecting the seepage force, because the water is going to push up the soil here. When the water reaches the filter, it's just going to flow normally. That's why it's a filter. So more weight, but not stopping the water. What we do is what? Adding this force. That's it. D1. This is the same. D divided by 2 times gamma submerged of the filter This is an added force. This is exactly the same that we calculated before. Exactly the same thing. Remember, this upward seepage force is acting only on the soil. That's why we don't include this D1 there. Calculate the factor of safety and we get this value. Basically, that's it. We are almost done with this chapter. I'm going to just mention this really quick, which is capillary rise in soil, and that will be everything for seepage. You know what capillary rise is. When you have a capillary pipe and you put it in water, the water is going to come up through that pipe. And that happens because we have what is called the tension, liquid tension, surface tension, and it's like pulling the liquid up in that part. And you can imagine that you have a situation like this because that's what is happening. You have basically a capillary tube here, and it's going to go up through the surface of the water. This is the tension. That tension happens around the fluid, the whole ring. That's what happens over there. That's why you have the meniscus of the water pulling it up. And it happens at this angle alpha that depends on the type of fluid that you have. Basically, if you see this sketch here, what is happening with the water pressure is from here and down, the water pressure is going to be H times gamma W. But if you go up, it's going to be a negative pressure for water pressure of HC times gamma of the water. And what the hell this has to do? I'm sorry, I didn't say that. Why in this world this has to do with soils? Because we don't have capillary tubes in soils, but we have voids in soils. And those interconnected voids can behave like capillary tubes. And that means that we can have a negative pore water pressure if we are in a capillary zone. If you do summation of forces in Y, at this point, basically what you're going to have is this, remember, the area, this is the weight of this part, the area of the water times the column of the water times the weight of the water. This is the weight of the water in this capillary tube, this part, going down. And what is going up? It's going this tension multiplied by cosine of the angle, because we're interested only in the upward force, multiplied by the perimeter of that pipe. From here you can solve for the capillary rise zone, which is HC, and as you can see, it's going to depend on this alpha and on this T, and of course on the diameter of the pipe. The T is the surface tension, and that depends on the liquid. The alpha is the angle of contact, that also depends on the liquid. D is the diameter of the capillary tube, weight of the water. For pure water and clean glass, alpha is 0, that means that is a pure tension going up in the rim, and tension is 72. This is 72 what? Newton per meter. If you put these values in here, you get the capillary rise of 1 divided by D approximately, and that's what we use basically for soils. What happened to our effects is, if you had a total stress here, this is the effective stress, this is the pore water pressure. When we calculate the effective stress, the pore water pressure is going to be affected now for these capillary rays, because we're going to have a negative effect in this part. That negative part is going to be the height of the capillary rise zone multiplied by gamma of the water. And it's affected also by how much is the degree of saturation on this part. Because that part, yes, it affects the degree of saturation. That's why we affect that value for partial saturation also. Now we have a force going up, water. But if it's not fully saturated, then the force has to be modified by that factor also. In one example, what I told you is this. This is not seepage force, remember. This is capillary rise. So basically what we have in this problem, we have a type of material here, and in this zone is prone to capillary rise and a height H2. And H3 is under the water table. You have dry sand. This part is clay with the small pores that allows, because if it was pure sand, it's not going to go up, never ever. You have to have a small pores there. So that's why you have clay, and this is submerged clay here also. Impermeable rock at the bottom. What happens here? First you calculate the properties of each one of the values, and secondly you start calculating this. What happened here? Let's start with the first one. At a depth 0, my total stress here is going to be 0. What is going to be the total stress at this point? Total stress at this, neutral stress and sigma stress. Total stress at this point. Total stress at this point is going to be this gamma, which is dry, multiplied by 8 feet, and you don't have any problem. What is the water pressure here? 0 at this point. If you look at this point from the top part, and the effective stress is going to be just this minus this. Now for this other part, remember we're going to have the same pressure coming from the soil, total stress, but at this point, due to the capillary rise, you remember this equation that I just showed you, the problem stated that you have 50%, I don't know if it's here, yeah, 50% of capillary degree of saturation in the capillary rise zone. So that's why you have in this equation the 50% of gamma of the water times this 4, and that's negative. 50% times this 4 times gamma of the water, that's a negative pressure. That means that if you look closely now, when I subtract this minus this, basically I'm adding this value. And that's important because in the zone of capillary rise, the effective stress is increased when you have a capillary rise. What happened at this point? 8 plus 4, exactly at this point, you have the 8 times 110 plus the 4 times 110. This part, I mean, when I say 110, I refer to this. Remember, I pointed to this, and the other 110 is this one. What happened with the U at this point? It's 0, because you remember the diagram crosses 0 at this point. And when I subtract this minus this, I get the same value here. Now when I go down, at this point, it's going to be 8 times this 110, plus this 4 times this 110, plus this 7 times this 117.44, and you get this value. And the gamma of the water, the pore water pressure at this point is going to be 7. This is submerged completely. 7 times gamma of the water, and you subtract this minus this, and you get your value there. That's the way the capillary rise will affect this problem. And then you build your diagrams. You see, this is the part that I was telling you, crosses 0 exactly here. This part is negative, this part is positive. That means that at this particular level, you have one value before and one value after. When you are in this part, in this zone, at the same level, but in this zone, you are still at this point. Now, when you move a little bit lower, the capillary rise is affecting it at that level, and that's why you have this jump in the diagram. I know it's a lot of material, guys, but you have a lot of time to check it also. And with this, you should be able to complete the other 2 problems from the homework, because the homework that I assigned had the problems for seepage and also had the problems for in-situ stresses. But this is the end of chapter 9. Now it's up to you. You have to go and you have to start checking and studying. That's it. If you have any question, let me know, and I'll see you on Monday. Have a good day. A good weekend also.